Assalamualaikum. Today we are presenting about indoor ultrasonic positioning and a navigation system, and we are presenting by Ahmad Zarif, Rahman, Mesbah, and also Atif. So the problem statement is that navigating complex indoor areas like hospitals can be frustrating due to unreliable indoor navigation such as unclear signage and verbal directions and lack of indoor navigation tools. This leads to confusion and unwanted delays. So our target user is first-time visitors and patients at hospitals. So our user need is precise location assistance, real-time tracking efficiency, clear and seamless guidance, and inclusive navigation support. So here are some of the supporting data on how often it is for people to get lost in hospitals. So here are some of the benchmarking solutions that we compare. So we mainly compare with Wi-Fi, ultra-wide bandwidth, other ultrasonics, GPS, and our solution. So what we have noticed is that comparing to others, ours is a lot more accurate, a lot more cheaper, disabled friendly, and it's easy to deploy, and also does not require a smartphone. So our unmet needs is that we must be accurate, it must be low cost, it must be disability friendly, and it's also offline and easy to deploy. So here is our value proposition. And here is our design specs, our must-have.
Right, so for design specs, in terms of user needs, here's our must-have. So in terms of precise location assistance, design attributes will be positioning accuracy, and to measure the mean error of measured position and real position, and our engineering target is to measure the distance for less than 5 centimeters. For real-time tracking efficiency, we want to make sure that it has a built-in location update rate, and the time taken to update the wristband location is relation to the listener, and the engineering target is 1 second per new guidance. So for a clear and seamless navigation, we want a multi-sensory feedback. We do this by having LED indicators and buzzer cues, and this is to ensure that we get visual and audio from our wristbands. Right, so these are our should-haves in terms of the user needs. So we have robust performance in multipath environments, affordable and scalable, and long battery life. So for our design spec, our could-haves are to have a simple setup and calibration, which we will showcase through our MVP later on. And then we have flexibility for upgrades and compatibility with hospital and minimal disruption, i.e. minimal interference.
This flow, it starts with the Bluetooth detection from the device, the wristband, to our phones. So we'll have a simple interface to select the destination to our phones. And then once you select the destination, the device will transmit an ultrasonic signal to the listeners. And then the listeners will send back information on the distance that is to reach the destination. And then that info will be sent back to the microcontroller in the wristband so that it can output corresponding navigation instructions through directional LEDs. So this is a block diagram showing the interactions between the components. So we have two microcontrollers working, one for the outputs, which are the LEDs and the buzzers. And we also have another microcontroller for the sensors, each for the wristband and one for the listener. And as for the setup, this is just showing the flow of how the navigation works.
So we want to get from here to node A. So the wristband will give directions to each listener. So from here, it will point to here, and it will point to here, and then point to here. So that's how it works with our wristband. And then once we arrive at the destination, it will stop giving directions. So here's the list of the items that we are using. And here's also the prototypes that how it should look like. And also here's a design analysis. So for the ultrasonic, we use it because we want high precision accuracy and zero interference. We're also using 3 listeners in order to get accurate guidance to the next location, and also a redundancy in case of listener failure. We are using ESP32 because we want to use ESP now as a backbone in order to help sync data across other microcontroller listeners as well, and also to allow Bluetooth communication between phone and wristband. For power, we are mainly using 5-volt wall adapters for the listeners, and also an 18650 2000 milliampere hour battery for the wristband. And then lastly, here is the test card. So for the test card, we're going to talk about the position accuracy. So for the position accuracy, we believe that we can measure the correct position of wristband and its relation with the target listener with a small deviation error that is less than 5 centimeters. So what this means is that, for example, if it detects that it's 10 centimeters away from listener to the wristband, the real life counterpart should also be 10 centimeters away. So to verify that, we will set up the prototype and put the wristband near the target listener. We then adjust the position of the wristband in relation to the listener, and then we measure the accuracy of the distance measured with real-life measurement. So we are right if the distance measured by the sensors between the wristband and the listener is similar to real-life measurement. And then for real-time tracking, we believe that the time taken to update the wristband location in relation to the listener is less than 1 second. To verify that, we will set up the prototype and put the wristband near the target listener. We then adjust the position of the wristband in relation to the listener. And then we will measure how long it takes for the position changes to be updated in seconds. We are right if the correct position is updated within 1 second. And then we also have user guidance and inclusivity. We believe that the system can provide clear instructions that users of different abilities can easily follow. To test that, we will test the prototype and see whether it can lead the user to the target destination through only visual or audio, and measure the percentage of users who reach the destination and the time taken to complete the route. We are right if at least 80% of users reach the destination and completion time is within 10% or better than traditional guidance. And then last test card that we have is robust performance in multipath environments. So we believe that the directional guidance given is accurate, consistent, and reproducible. To verify that, we will test the prototype and see whether it can give the same directions regardless of where the starting point of the user is. And then we will measure how often it gives the same directions to get to the target destination. We are right if it gives more than 90% correct directions through all the trials. All right, and that is for our slide. Now we will go to the demonstration. Thank you.
Okay, so this is the whole wristband. Here we have ESP1 and we have ESP2. ESP2 is basically the brains of the whole operation, and ESP1 just handles the timing. Initially when we start the wristband, there's a calibration phase. After which, when you select the listeners, you can select the listeners via Bluetooth, or you can just use the switch here, just for demo purposes. You can use the switch, like imagine I do this. This is listener 1, this is listener 2, and this is sequential. So no matter what I say, this one will send the signal to this one that, yeah, connect to listener 1 or connect to listener 2. So when it sends the signal, this one connect to listener 1 over ESP now, and then they will like sync up, using the ultrasonic and ESP. They will talk and they will figure the distance out. And the next step is when these are facing each other, it sends a pulse to this one. So when it sends a pulse, this thing will remember. Like this is the MPU 6050. It's a gyro sensor, gyroscope. This will remember. You can just lights. Yeah. So the gyro, these are the for the facing. The center one is facing exactly. If you're facing this way, this one will light up that, yeah, you have to turn back left. If you face right, this one lights up like you turn back right. And if you're like facing up or down, then these two light up, like show you that, yeah, you're facing up or down. And all that just shows like, is it what mode is it in? So these are all the components, and just show the listener, I guess. Right. So this is the listener. That's it basically. It's just a ESP32C3 with a HC-SR04 ultrasonic sensor connected to it. There's a voltage divider, as you can see, because this runs at 5 volts and ESP30 runs at 3.3 volts. So yeah, that's it. This is just the listener. That's it. So like this way, like when they're facing, then it does the logic and everything. So, right. So it's currently set to sequential mode.
Yeah, sequential mode. So sequential mode means that once, for example, right now we want to go to this location, but in our path we have to cross this first, and then we go to this one. Like imagine like a corner or something like that.
Yeah.
And then for now, it's telling me first I have to actually see it first for me to get a direction. So so now that it sees it, it's now giving me direction to go here. So once I go here and get closer, right? It blinks. That means that I've arrived to the first checkpoint. But now I need to go to the other checkpoint, which is right here. So we need to recalibrate first the positioning, and we need to actually see this guy first before we get a direction. So let's see the guy
a bit back,
a bit back. Okay, now it's facing each other. Now wait, hold on, is it?
Yeah, it's facing. It's not updating.
It's not updating the actual location, but whatever it is, the light's supposed to point to here. And then once we arrive, it will blink to show that you've arrived.
Yeah, so that's standby.
So this is our test card. Over here, we are trying to test the distance measured and also the real life distance. So on the tape measure, it will say 46 or 47 centimeters away. And then on our serial monitor, it will also say 47 centimeters away. Alright, and now we want to test the directionality guidance that it gives. For example, when we change the direction, the lights also will change the direction to show you where is the proper direction to go to the listener. And then as we get closer, the distance will also change as well. So right now, it will change that, and you can see how fast it updates. That is also the update speed, the update rate. So thank you, and that's all for our presentation.